All right, in this video, we're just going to continue on with some more calculations, but this time the calculations are going to look at something called molar volume. So the volume per mole of a particular compound or element. So the molar volume of a gas is the volume occupied by 1 mole of the gas. So molar mass was the grams per 1 mole. Molar volume is the liters or the mils per 1 mole. So at something called STP conditions, standard temperature and standard pressure, the molar volume is always 22.4 liters in 1 mole. So this is a new conversion factor. Now, some of you may notice in IB chemistry, the molar volume is defined at 22.7 liters because their standard temperature and their pressure is a little bit different. Okay, so we're going to go with a 22.4 liters. Just a quick thing before we jump into calculations. Remember, Avogadro's hypothesis states that equal volumes of different gases at STP will have the same number of particles, which is 6.02 times 10 to the 23. So the conversion factor for this lesson that you have to keep in mind is when we're dealing with gases at STP, the conversion factor is 1 mole over 22.4 liters, or you can say 22.4 liters over 22.4 liters over 1 mole. So let's just fix it up there. Okay, let's try some calculations here. So what is the volume occupied by 0.850 moles of NO2 at STP? So we're going to say the volume we want in liters. And let's go ahead and set this up. So we're trying to calculate the volume. So we'll just write down volume in liters of NO2. And then we write down the initial amount that we're given, 0.850 moles of NO2. And this is at STP. So we want to get rid of moles. We want to get to liters. So we want to make sure that the moles are on the bottom and the liters are on the top. So 22.4 liters for every 1 mole. When we work through this, the moles cancel out. And you're going to find that you have 0.85 times 22.4. And that's going to be 19.04 liters. But got to double check the sig figs here. So this is 3 sig figs right here. Now the 22.4 liters, even though it's a conversion factor, that number is a measured value. So you do have to consider the sig figs for the 22.4. So that's going to be 3 sig figs there. So our answer has 3 sig figs, and remember to include the name of the chemical as well. Okay, so don't just write 19.0 liters, write 19.0 liters NO2, nitrogen dioxide. All right, let's take a look at the next one here. So how many moles of gas are in a balloon with a volume of 15.0 liters at STP? So once again, we know there's this hidden conversion factor, 22.4 liters per 1 mole, or the 1 mole over 22.4 liters. So anytime you see the word gas and STP, right away you can start thinking of this conversion factor. Okay, so let's go ahead and set it up. So we're trying to figure out the number of moles of this unknown gas. We don't know which one it is, so we'll just write down gas. And we are starting off with 15.0 liters. And we want to get rid of liters. We want to get to moles. So let's just use the red color here. So 1 mole has 22.4 liters. Working through, you find that the liters cancel out, and you're left with 0.670 moles of gas. And in terms of sig figs, you've got 3 sig figs here in the 15.0, and then 22.4 is also 3 sig figs, so your answer should have 3 sig figs. All right, one more practice here. How many moles of gas at STP are in 45.0 liters? So go ahead and work this one out. Just pause the video. And then check your answer. Okay, and there's another question there. What volume is occupied by 2.60 times 10 to the 3 moles of a gas at STP? Once again, try this question and then check your answer. And okay, so the next thing that I want to go over is calculations involving moles and particles. So remember we talked about how many things are in a dozen. One dozen has 12 items. How many particles in a mole? 1 mole has 6.02 times 10 to the 23 particles. So get used to saying that. The more you say that, the more comfortable you're going to be with this conversion factor. So the conversion factor we have here is 1 mole over the number of particles, or you can put the particles on top and the moles on bottom, depending on what you're trying to cancel out. So let's go ahead and try this. How many molecules are in 6.72 moles of CO2? So we're trying to figure out, I'm just going to make a quick addition here. You can say particles or molecules. So you can interchange those two. So we want to figure out the number of molecules, and we're given 6.72 moles of CO2. We want to get rid of moles, so they would go on the bottom, and particles go on top, or molecules. So in 1 mole, we have 6.02 times 10 to the power of 23 molecules. So working this out, you're going to find that you have, let me just punch this in and cancel out what I don't need. You're going to find that the answer is 4.05 times 10 to the 24 molecules of CO2. In terms of sig figs, how do you come up with sig figs for this one? You look at the total digits here in the 6.72, that's going to be 3 sig figs. And then this conversion factor, Avogadro's number, is once again a measured value, and it's just been rounded up. So therefore, this is considered in sig figs. So we have 3 sig figs with Avogadro's number. So the final number of sig figs we can have is 3. So that's why we have 4.05. All right, let's look at this one here. So how many moles of carbon are in 5.60 times 10 to the 18 carbon molecules? So we want to figure out the moles of carbon. We're starting off with 5.60 times 10 to the 18 carbon molecules. We want to get rid of molecules, and we eventually want to be in moles. So we're going to say here, molecules on the bottom, and then I'll plug in the numbers after, and mole on top. So we know we have Avogadro's number, 6.02 times 10 to the 23 for every 1 mole, so molecules cancel out, and you are left with moles, and then you just work this out. 5.60 times 10 to the 18 divided by Avogadro's number, and you should get 9.30 times 10 to the negative 6. And once again, this is going to be 3 sig figs because we have 3 sig figs in all of our starting values. Okay, so now in this question here, so this one's a little bit different. So it's saying here we have 16 molecules, but we want to get to atoms. Okay, we don't want to get to moles or volume or anything like that. So this one, let's set it up carefully and make sure we understand what it's asking and how to get there. More space here. Okay, so we want the number of atoms in that particle. And we're starting off with 16 molecules of CH3Cl. And the conversion factor for this one is going to be in 1 molecule of CH3Cl, how many atoms are there in total? So what you have to do here is you have to count up all the atoms. So you have 1 carbon, 3 hydrogens, and 1 chlorine. So you have a total of 5 total atoms. Okay, so this conversion factor is one that's always going to be different depending on the type of compound you have and how many atoms you have. So you always have to just count up what it's asking for. So when you work through this, you get 80 total atoms. And in terms of sig figs, you would say, okay, the 16 molecules, we have 2 sig figs because that's something that we measured. Now the 5 is a counting number. It's a nice whole number, and you can't have like 4.5 atoms. We counted exactly 5 atoms. So you don't consider this one in sig figs. So do not count sig figs for this for the 5. So we have 2 sig figs here, so we can either go 8.0 times 10 to the 1, or we can just put a bar over top of that to show that that is significant. The next part of this question was how many hydrogen atoms are there in 16 molecules? So now instead of looking for total atoms, we're looking for just hydrogen. So how the conversion factor is going to change here is you're simply going to focus on just hydrogen. So it would look like this. You'd say in 1 molecule of CH3Cl, you have a total of 3 hydrogen atoms. So we're going to write down 3 H atoms. Okay, so that's the only difference there. So here we're looking at just hydrogen. So then your ratio would be, your conversion factor would be 3 over 1. And in terms of sig figs, once again, you don't consider the 3, you only look at the 16, and that's 2 sig figs there. So your answer should be 48 hydrogen atoms.